Let's discuss products of rings. So, given two or more rings, their Cartesian product becomes a ring under slot-wise operations and obvious 0 and 1. So, what more is there to say? Well, the point is often not so much to take the product of given rings, rather, given a ring R, how do I recognize if it's isomorphic to R1 cross R2 or at least related to R1 cross R2? Because then I can try to understand R in terms of R1 and R2. For us, the main point of products is to characterize them in terms of idempotents and see how they come up in connection with the Chinese remainder theorem. To reach our goal, we need to understand products both internally and externally. Let's begin with the external view. This means I do not look so much inside the product but at the maps in which it participates. The very first such maps are projections onto R1 and R2. Note that these are surjective ring homomorphisms. For later use, let's just note down the kernels. For projection onto the first slot, the kernel consists of 0, anything, which I have written over here. And similarly for kernel of the other projections. Okay. Next, let's see the universal property of the product ring. So, suppose I am given a ring S and homomorphisms from S to the rings R1 and R2 called F1 and F2. Then the claim is that there is a unique ring homomorphism from S to the product ring that matches F1 in the first slot and F2 in the second slot. More formally, I want a map which when composed with pi1 gives me F1 and likewise for F2. Okay. So this is just straightforward set theory. This map is forced upon me and you check that it is indeed a ring homomorphism. Alright. Why is this called the universal property? For the same reason as in the case of polynomial rings and quotients. Namely, this property characterizes the product R1 cross R2 up to a unique isomorphism. You do not have to understand the statement that I just made, but you do have to be able to use this statement. What it gives you is the following. Suppose I have maps from a ring to R1 and to R2. Then I naturally get a map to the product. Okay, so it's nice to have this external view, but I need to be able to understand the ring internally also, the product ring. And for this, key elements are idempotents. So an element E is called an idempotent if its square is itself. So in this ring, you should look for idempotents. You will find that there are some trivial ones and some non-trivial ones. Look for interrelationships among the non-trivial idempotents and see if they have anything to do with these kernel ideals. So please do this now. E square equals E means E times E minus 1 is 0. In a domain that would force E to be 0 or 1. These are called trivial idempotents and they are there in any ring. But in R1 cross R2, there is a non-trivial idempotent 1, 0, which I call E1, and also 0, 1, which I call E2. These are crucial to understanding the product ring internally. In fact, a ring is isomorphic to a product precisely when it contains a non-trivial idempotent. In the forward direction, I already saw E1 and also E2. In the backward direction, from the ring S and D1, somehow I have to get R1 and R2. So, I look towards the product for a hint. Here, R1 is not even a subset of this, but there is a subset just like R1, namely R1 cross 0. This is not a subring of the product because it does not contain 1 in the larger ring, but it is closed under addition and multiplication. In fact, it is an ideal of the larger ring. But it is also something else, namely, it is a ring in its own right, just with a different identity, namely E1. Okay, and as a ring, it is isomorphic to R1 just by dropping the 0 in the second slot. How do I get this ring from R1 cross R2? Just multiply by E1. So this gives me a strategy. I try to show that S is isomorphic to S times the given idempotent cross S times D2. How should I find this other idempotent D2? I again look back for an idea and see that E2 is 1 minus E1. So I try to take D2 to be 1 minus D1. Now I have to find a map in the appropriate direction and check that it's an isomorphism. This is not difficult, so try to do this now. This is a matter of verification and I have written the steps over here. First, 1 minus any idempotent is always an idempotent. You should check this quickly. Therefore, the sum of these idempotents is 1 and their product turns out to be 0. So I have a symmetric situation with D1 and D2. Next, Di times S is a ring in itself with identity Di. This is because DIS is an ideal, in fact the principal ideal generated by Di. So it has addition, subtraction and multiplication. Di works as identity on this ideal because Di is an idempotent. Next, I have a ring homomorphism from S to DIS, which is multiplication by Di. Addition is preserved because of distributivity. 1 in the source goes to Di in the target, which is identity there, and multiplication is preserved again because Di is an idempotent. Okay, now that I have two ring homomorphisms from S, I combine them to get a homomorphism to the product. I claim that this is an isomorphism. To check injectivity, let us see the kernel. If A is in the kernel, that means that D1A and D2A are both 0. So their sum is 0. And now I remember that D1 plus D2 is 1 to conclude that A itself must be 0. For surjectivity, take an arbitrary element in the target. Now I claim that D1A plus D2B is mapped to this element because when I multiply this by D1, the first term survives because D1 square is D1 and the second term dies because D1 D2 is 0. And similarly for the second slot. And my proof is done. Okay. In the midst of checking these details, don't lose sight of the overall strategy. I express the ring R1 cross R2 in terms of its idempotents. And then I try to recreate this same structure inside S using the given idempotent. That's why all of this worked. Alright. Now, in the first lecture, I said that these three elements form a ring inside Z mod 6Z, but it is not a subring. How did I get this? I just used the idempotent 4 bar inside this ring. Similarly, using its partner idempotent, I get another ring. And the upshot is that Z mod 6Z is isomorphic to Z mod 3Z cross Z mod 2Z. For us, there is nothing more to say about product rings on their own. But like with any tool, it's interesting to see how it combines with other tools. Here is a common way to use products. Suppose I have ring homomorphisms F1 and F2 from a ring S to rings R1 and R2. Then by the universal property of R1 cross R2, I get a homomorphism from S to that ring. Now, see what the first isomorphism theorem has to say about this homomorphism. For that, you will first have to find its kernel. So do that now. A is killed by the product map precisely when it is killed by both F1 and F2. So, the kernel of the product is just the intersection of the individual kernels. By the isomorphism theorem, F1 cross F2 induces an isomorphism from S modulo this kernel onto the image of the product map. Sometimes the product map is surjective. In that case, the isomorphism is onto the entire product. For example, this happens in the Chinese remainder theorem, which is an important homework problem. Okay, but a particularly important special case you should do now itself. And this is the map pi, which is the product of quotient maps onto R mod AR and R mod BR. where R is a PID and the GCD of A and B is 1. Okay. See what this says in the given situation. For that, you will have to calculate the kernel and the image of pi. But before that, remind yourself how GCDs work in a PID by completing this line. So do this now. In a PID, to find GCD of A and B, take the ideal generated by them. It is principal, so has a generator D, and I claim it works. Why? A and B are both in this ideal, so the generator D divides both of them. D itself is of the form AU plus BV, so any common divisor of A and B divides it, and thus D is a GCD. You have seen this argument multiple times starting with homework 0, and it should be at your fingertips. In the given situation, I can write 1 in this form, and I claim that the map pi is surjective onto this product and its kernel is generated by AB. So by the isomorphism theorem, I get this isomorphism. You should aim for the ability to do these proofs on your own. So try it now. This equation is crucial. The kernel of the product map is the intersection of individual kernels of the two quotient maps. So it consists of common multiples of A and B. AB is such a multiple. In fact, I claim that it generates this intersection. Why? Take a common multiple L and multiply this equation by L to get this one. Now I notice that both LA and LB are multiples of AB and therefore L is also such a multiple. Okay. Next, for proof of surjectivity, I have this neat little argument. To understand and remember this, you really should work through this on your own. The key is to first get idempotents in the image and then use them to see that everything is in the image. So pause if necessary and work through this. Okay, let's do exercises. I have asked you to analyze this quotient where the field F is one of these three options. In practice, you have to recognize when this theorem is applicable. If it is not, then you should identify what the relevant tool may be to understand this ring better. So do this now. Before we discuss exercise 1, note that the usual Chinese remainder theorem, where a and b are coprime integers, is a special case of this, and you did it already in homework 0. In exercise 1, fx is a PID. So let's see if this theorem applies. Over complex numbers, x square plus 4 factors into distinct linear factors and their GCD is 1. So, by the Chinese remainder theorem, I get this isomorphism. But note that this factor is Cx modulo a linear polynomial. So, by evaluation at minus 2i, I get this to be isomorphic to complex numbers. And similarly for this one. So, I get a product of fields. Note that this is not a domain because of the non-trivial idempotents. Next, over real numbers, x square plus 4 does not factor. So going modulo it gives me a field as we saw in the last lecture. But I can see this directly. Take the inclusion from real numbers to complex numbers and extend it by sending x to 2i or to minus 2i. In either case, I get a surjective homomorphism and the kernel is generated by x square plus 4. So this quotient is isomorphic to complex numbers. Over f2, x square plus 4 is just x square. This polynomial factors, but now into repeated factor x. So when I go modulo that, I get a nilpotent element x bar. This is non-zero, but its square is 0. Notice that such a thing is not possible in a field or even in a product of fields. So this is a completely different kind of ring. Now you should be able to carry out similar analysis for fx modulo a monic polynomial over any field f. So try to do this on your own. For now, let's go to exercise 2. Rt need not be a PID, but still this special polynomial factors into distinct linear factors, and I can write one as their linear combination. So everything works just like before, and the given ring is isomorphic to this product. Both of these are isomorphic to R by evaluation at 0 and at 1. Or I can do this by hand by taking the product of these evaluation maps to R cross R and checking that it is surjective with kernel generated by this polynomial. So you can check the details. Next, try to relate this ring to a product of known rings. Notice that the polynomial in the denominator factors. So try this now. This polynomial factors as x plus 1 times x square plus 1, suggesting evaluation at minus 1 and at I. So if I take the product of these evaluation maps from Zx to Z cross Gaussian integers, then this polynomial is in the kernel. In fact, every congruence class here by long division by this polynomial can be represented by a quadratic polynomial, giving me a formula for phi. Using this formula, check that phi is injective, but it is not surjective. The image of phi is given by all expressions where r plus s plus t is even. You should check this. So, the image of this map is a subring of this product, and this phi is an isomorphism onto this subring. Artin has given another example like this. If I had taken q instead of z everywhere, then half would be available to me, and this map phi would have been an isomorphism. Some final remarks, and you should take these as exercises. Suppose I want a ring with exactly 21 ideals. Well, take a prime p and then z mod p to the 20z works. You should justify this using the correspondence theorem. But suppose I want different types of rings with this property, maybe with a desired characteristic. Then this fact may help. Ideals of R1 cross R2 are precisely ideals of R1 cross ideals of R2. This is completely false for groups. For example, the diagonal subgroup of Z cross Z is not a product. For the proof, it is easy to see that all of these are distinct ideals of R1 cross R2. But why should a given ideal of R1 cross R2 be of this type? And how do I get the corresponding I1 and I2? The answer is again use idempotents. I have written the argument here, but really you should do this for yourself and explain more by writing explicit elements. Okay. Next, at some point, I asked you for a non-zero polynomial over an infinite ring R that defines the zero function on R. Such a thing is not possible over an infinite domain because there a non-zero polynomial can have only finitely many roots. But such a thing is indeed possible over a finite domain, and in fact we characterize such polynomials. So now see if you can use a cheap trick to get a required example. This note about self products may also give a hint.